session and to catch up with that. Okay, so we were discussing mutation testing. I'll go over that again just for a quick recap, really quick, and then we'll go to operators. I think this part is what we were left with. I think some of the definitions within mutation testing is also pending, and that has to do with infection only. I mean, that is the topic that we intended to discuss anyway, but coincidentally, it happened that that is the exact point where we left in the previous class also. So, from the perspective of the exam, also the upcoming exam, it is going to be helpful as well. So, I think most of this is already discussed, right? So, I would advise everyone to go through the previous recording if they want to, you know about these things. Okay, so I'm assuming that this background is, already discussed. So now moving forward with whatever is left from here. So this part is what I was discussing in the previous class, and then we closed at this point. So again, recapping from here, so you understand what mutants are. Mutants are some single change. You have a ground string that is a source code. You make one change that you get a mutant, right? So how many ever changes you have, that many mutants you have. And remember, in mutation testing for programs, we generally consider one mutant at a time. So you make a change, you get one mutant, and then you go back to the ground string again, meaning you start again with the ground string and then make another change, and then that's why you get two different mutants. Okay, so you don't apply multiple mutants at once. That is the assumption that we are going to make in this case. However, there might be special cases wherein multiple mutants might possibly be considered as well. But for our discussion, the assumption is going to be that we are considering one mutant at a time. That is, on the ground string, you're going to apply only one change. And every time you apply a change, single change, that is going to be considered a new mutant. Okay. Now, there are various types of mutants that we discussed. Right. Some of them, as mentioned here. So, you know, and what we are looking for is mutants that are valid and can be killed by a test case, meaning you make a change and such that you can have a test case so that that change, that mutant is killed. And I hope you remember what the definition was for killing a mutant. That is basically, so initially we said, what initially we said, we'll go to refined notions about killing mutant also. Some of the notions that we've defined earlier, we're going to refine it as the next slide says. But before that, just for a recap, so we said that if the output, so you are having a program P, test case T, okay, and a mutant M. Okay, so small m maybe a mutant. So you have a ground string, you make a change, you get a mutant. So I'm talking about one mutant only. So let's say I have M, the mutant, ground string, that is P, the program itself, and I have a T. So the test case T remains the same. So I have a test case, meaning what is the test case? Test case is having inputs, uh, expected outputs, right? So I'm having input. So if I give this input, then I expect that the actual output will be this. Right now, again, if the actual output matches the expected output, then we say the test case is passed. If they do not match, then we say the test case is failed, has failed, right? So that is the idea that is quite general. Okay, now here also, so since we have a mutant, we say if the output of the mutant and the output of the ground string, so we run the test case on the test case is same. T is same. We're going to run the test case on both the mutant as well as ground string. Remember, mutants are another program. We can also compile it and run it. Okay, we are considering that mutants are syntactically valid and therefore they can be run also. It's just that we have made some changes. So, for example, you were doing somewhere, down the line, some if condition was there. Maybe you were doing greater than zero somewhere. So instead of greater than zero, you made a change. You made it greater than equal to zero, right? So that therefore you get one mutant, right? That is how we make changes. And this background we have discussed already. Now, so if we run the test case, if it so happens, according to the definition that we have considered so far, up until this point, is that if the output of the mutant is different from the output of the program on the same test case T, then the mutant is set to be killed. That is, in other words, if you're getting the same output from the test case T on the mutant and on the program as well, then that mutant is not set to be killed. Okay, that is not killed then in that case. What you have to do to kill the mutant is to make a test case, to come up with a test case, because test case is variable, right? We are just saying that you should have a test case such that the output becomes different in both these things, right? Both of these things, that is the program and the mutant. If that happens, then the mutant is killed, and that is the idea in mutation coverage also. You want to have test cases so that all the mutants are basically killed. That is, you are able to produce the output that is different on the program and on the mutant. Now, some of the mutants are trivial in the sense that it is so different in some sense. This change is so kind of different that it can be killed by any test case. For example, maybe let's say you are having a print statement at the end of the program or the function whichever you want to test, right? Now assume that that message was a constant string, some string, right? So I say program ended, right? So this is like system.out.println program ended. So what is the going to be output? Program ended will come in the program, right? And I make the change in that constant itself, the message itself. Then I say program ends here. So I still get a mutant, right? I mean, that's a change if you think about it. Of course, that's not useful. That is not a useful change. So how do we make useful change? That is where mutation operators help us. Okay, so we'll discuss mutation operators later, but just to give you an idea, I'm still getting a mutant because the idea was to make a change. Okay, so I made a change. Now what happens? Since the final line, the print statement I'm changing, obviously the output is going to be different. It's so obvious change, right? The output is of course going to be different, regardless of the test case. Whatever test case or whatever input I do, since the final message is changed, I've changed that, right? So I'm printing something else. So of course, if you observe only the final output, then that is going to be changed. So in that case, it's a trivial mutant. That is, regardless of the test case you are running on, it is going to be always killed. The output is always going to be different. So this is also not useful for us. Okay. Still, more mutant is one such kind wherein it is invalid. That is, syntactically invalid, so it cannot be compiled. I think we discussed it. So this is also not useful. Equivalent says that even if you have made a change, it is equivalent to the functionally equivalent to whatever was happening in the program. So let's say you just change the name of the variable. Okay, so instead of, let's say, integer n is equal to 10, I am saying integer a is equal to 10. Now that is the only change I make it everywhere, of course. I make the change. Now it is equivalent, right? Even though I made a change, it is not going to affect the program. The behavior is going to be same always, right? Variable names do not matter, right? The functionality is going to be same, right? So that therefore it is equivalent, and there are other ways of getting to equivalent mutants. I think some of which we discussed in the example, but this is also not very useful because no test case can kill them, right? This is obvious because in this case it is same as the ground string, right? Only some of the things are changed, which is not actually causing a functional change in the program. Therefore you cannot expect to get a different output, and therefore there cannot be any test case that can kill it, right? So these three is something that we are not looking for in mutation testing. What we are looking for is known as, oddly enough, but this is the official terminology, dead mutant. So basically it says mutants that are valid, meaning syntactically valid, that can compile. First of all, you have to run it, therefore you can run the test case, right? If they're not valid, then you cannot run the test case, so that's okay. And can be killed, meaning there exists a test case such that if you run that on the program and run that on the mutant, those outputs are different. So therefore we say that can be killed by a test case. So any test case you take, you have to produce a different output on the mutant on the program. Only condition is that the test case remains the same, both cases. So I have only one test case that is being run on both the mutant and the ground string. Okay, be careful with this part. Okay, and these are the only useful mutants for testing. We are going to kill all those mutants that are uh, you know uh, basically the dead mutants that are there. Okay, so with this idea in mind, so far I said only about the output, right? I said the output is different. You said the mutant has been killed. That is the notion of killing so far. Now we are going to move forward and see this part where it says killing a mutant, refined notions. So we are seeing some refinements over the earlier definition about killing, and we'll also see and try to motivate the idea of why this refinement is even needed, right? I mean, can't we have the simple notion of observing just the output? But if you understand from the previous some of the earlier discussions that we were having regarding infection, propagation, and all that, you might be able to realize that it is not always possible to cause a different final output. Okay. However, the state of the program may change. So I'll maybe take a step back and try to explain that as well. Anyway, so let's go with the definition first, and then I'll elaborate on that later. So basically, it says, as defined earlier, make it difficult to create this all the time because it says it's a strict condition, right? It just says the output must be different. Now, in most of the programs, I would say, most of the reasonably large programs, it is not possible to always cause a change in the output. Maybe your small mutation, small change somewhere in the source code might cause some behavioral changes inside of the program. It might cause some state changes, it might cause something else. Maybe you were trying to write something to the disk, maybe you are creating a file or something, so maybe you change, because of the change something else happens. The data that goes in the file might be different or something like that might happen, but the final output of the program, if you are reading the file again, then of course that is going to be changing the final output also. But what I'm saying is that in general, it's difficult to have a final output which is different, right? Maybe something happens internally, but we are not able to observe it on the outside. Observing here means able to see it on the final output. Okay, final meaning the thing that you see at the end of the program under test. Okay, so therefore it is difficult. I mean, it is difficult. I mean, at this point it might not be very clear as to why it is difficult, but hopefully as we move forward it will become clear. Why it is not possible to have uh, you know final output which is different. Okay, so we are trying to just relax this a little bit, relax this condition. Now we are saying that there are two ways you can have killing mutants. Okay, so this is the original definition. Therefore, we're saying recap. This part I think I mentioned already. Given a mutant small n belonging to capital N for a ground string that is program p and a test t is set to kill him. Okay, if and only if the output of t, now output meaning the final thing, so the final output that you see of t on p is different from the output of t on m. This is what I described so far. It's fine. But it says then we are trying to refine now. We are saying this is not good enough. We are saying that okay, this is difficult, right? How do we create test cases such that the final output changes? Maybe I'm able to affect the program in some way or the other, but I'm not able to observe in the final output. Maybe it can happen, right? So let's say employee example, right? So maybe you had an employee object, and so the program might be printing employee name and age, let's say at the end of. I'm just giving you one arbitrary example to get the point across. So let's say I am having employee object, and the program what it does something. It creates an employee object and so on, sets the name and the age and so on, all the properties. And it is the idea is to print the name of the employee and the age at the end of the program. So I'm going to print that, and it not necessarily be a printing only. I'm just saying that that is what I'm seeing on the outside, right? Now I have other attributes also. Let's say department. So I made a change in the mutant or salary, for instance. So salary may be defined based on some conditions, right? So if the employee's grade is greater than so on and so forth, then the salary is this much, else this much, and so on. This is what you do. Now I'm going to mutate it. I change the condition. So I say grade instead of greater than 7, I make it greater than 8 or something like that. Some greater than equal to 7, something like that. I made a change. Now because of which the employee object, the salary is changed now. Salary is different. No, earlier for the same employee on the same test case, I was creating an object and the salary was something. No, because on the mutant the salary is different. So for that employee, so you are having a different object. But on the outside, the name and the age is same. So I'm going to print name and the age. So if you see only the output, the final output on the mutant and the final output on the original program, you're only going to see the same name, same age, and on the mutant also you have the name of the employee and the age thereof. So it's the same thing, right? It is going to be so in that way the final output is still same, right? Even though the salary was different because but since I was not printing that, I was not able to observe it. So it's a very trivial example again, I know, but this is just to get a point across that the final output might not always be different, even though there are some internal changes that happened and you were not able to realize that. Okay, so therefore we are trying to relax this notion of not only seeing the output and not only seeing the final output, rather we are also seeing the state of the program. Okay, so I'm assuming that most of you will be familiar with this notion of the state of this program at this point. We have discussed this, I think a lot of times, but particularly in symbolic execution, we've seen state of the program, right? How it changes. So you are at line number 1, variables are being defined, values are being assigned, and so on. You have a dictionary, that manages the state, the concrete state of the program, and so on. However, here we are talking about concrete state. Okay, there we talked about symbolic as well as concrete in the case of concolic testing. However, in this case, we are talking about the general notion of the state of the program. So what happens is that in memory, just a quick recap as to what a state is. In memory of the program, you have something, some state, the current state as we call it, right, of the program. As it changes, as the program runs through, as it is running, the state is changing. The state is dynamic, right? So maybe you have I is equal to 0, so you are running a loop. So initially at time t, maybe you have I is equal to 0, then one iteration of loop completes, then you are having I is equal to 1, right? So that state changed now. The state is that, right? The state is the internal memory. The basically we call it a state only, right? So the information that is stored in the runtime state of the program. What is the current state? So these things change, right? As and when the program runs. So some variables were earlier not defined. Then I reach line number 32. Maybe at line number 32, I'm defining some variables. So those variables were not there, and now they are in the state, and so on, right? The values are getting changed. So I'm doing some addition, multiplication, and so on. So these things are dynamic. Every time the state is being changed. So the current status of the variables within the program, I mean, very naive definition is something like that of the state. Okay, now I can have a discussion about the state only, uh, but that will take a long time. So rather, I'll go to the definition for this one. as regards killing the mutant, and we'll try to compare and contrast, and we'll see where the difference is. Okay. Now, so this recap is over. So what it is saying that it may not be necessary to see the change only through an output all the time. That is what I said. No, final output, the employee example I gave, right? The final output might not change. How do we know whether we have killed the mutant or not, right? In fact, by this definition, if you go, you will see that you'll not be able to kill it if the final output is not changing, and therefore it is difficult, right? Because I cannot have a test case maybe that can change the final output, right? So then we are refining it. Okay. So it says just reachability and infection are enough. Reachability says we have to reach that. So for example, I had a program and I'm going to mutate at line number 3. Okay. So let's say line number 3 was under a condition. Now, if that condition is not true, due to which you reach line number 3 where the mutant is, where the change I made, right? Somewhere down the line I made the change, right? Now, if those conditions are not true, then how can I reach that? That is what symbolic execution was trying to do. Symbolic execution was trying to reach that, right? Reaching different portions of the program. How do I reach? How do I reach error? So in this case, we are not trying to reach error, rather we are trying to reach the mutant. Okay, so if I make a change somewhere, but my code is such that my input is such that I'm not going to reach that particular place of change, then there is no point in having that change, right? I made a change so that I can possibly see how to kill that mutant. Now, if I'm not able to reach that particular line where the change is made, then it is of no use, right? So therefore, reachability is important in both the cases. Of course, for the output also in the original definition also, but here also in the refined notion, we have to reach first of all. And second point, it says so two things are there, right? So this one talked about the final output. Okay, try to contrast the two. I'll try to clarify some of the things that might not be very clear at this point, but bear with me for some time, please. So what I'm saying is that this is about the final output. Now here we are trying to say, just reach the mutant, just read the change line, the line which is changed, and try to infect the state of the program. Infection is what it is. Okay. Infection says that the state of the program is different. So we'll see that moving forward. This was talking about the final output, right? And this is talking about the state. So these two things are different. We'll come to that. Propagation may not be necessary. Propagation says, so these three things actually go hand in hand, basically. First thing is reachability. I made a change, or let's say talk about error, right? I have an error somewhere, some mistake is there in the code. So to be able to realize that that mistake exists, a test case need to reach that statement, right? That means all of those earlier conditions that are there before that needs to be satisfied. That is what symbolic execution was about, trying to reach the particular place. Okay, so that is one thing you always have to do that. Then only a test case is useful, right? Otherwise, how do you test? The second thing is infection. Infection says that the state of the program must change. Okay, this part is what needs to be clarified a lot, and I'll come to that. Propagation is about the final output again. So what happens? The sequence is something like that. You reach, okay, a particular place. You infect. That is about mutant. Okay, mutant basically causes an infection in the state of the program, and then propagation may or may not occur because of this infection. So reachability is still satisfied. You have to reach it first of all. Then you are going to infect. If you're trying to kill, you're going to infect. Then it might propagate or might not propagate. So this part, the earlier definition about killing mutant that says about the different output might not be always possible, right? So what we are saying is that instead of requiring all three, this part was actually requiring all three. It said we have to reach, infect, and propagate. Propagate to what? Propagate to the final output. Meaning the change is such that you're able to see the final output even changing, right? So maybe in the employee example, if I were to do something with the name, then I'll be able to see it in the final print statement also, in some sense, right? You get the idea. So basically that's what it is. So this propagation is what caused the change in the final output, meaning the last thing that comes out of the program. Okay. However, what we are trying to say now, we are trying to relax it a little bit because that was difficult. We just say, okay, just do reachability and infection. That is, we need not propagate. If we are able to propagate, that is good. That is good. This notion is still valid. If you are able to cause a change in the output, that's fine. If you're not able to cause a change in the output, that is also fine. Okay. So this part we're trying to refine a little bit. We are saying that propagation is optional now. You need not change the final output. If only the state is changed, that is fine. Okay. One side note here, I just like to point out is that without infection, there is no propagation. There cannot be propagation at all. Okay. Because what you see on the outside, what you see as an output of the program must be something which is in the state of the program. If you try to understand it so far what I've been explaining about the state of the program, right? Whatever comes out as the output must be something from within the state of the program, right? So in that way, if you're not able to infect, meaning if you're not able to change the state, if you're not able to affect the program in any way, there is no way the output can be different. You see? So in that case, infection is necessary for propagation to happen. Okay. But if infection happens, propagation may or may not happen. Okay. And on this part, we are going to refine this notion of killing a mutant as well. Yeah, here. We refine killing a mutant and coverage to reflect this change. Now, before I move forward, I just want to take a quick break and take questions maybe because this part might be slightly ambiguous. So I was hoping to have a little bit of feedback from you as well. Yeah. So any questions so far? Is the idea that I explained somewhat clear?
Yes, somewhat is
Okay.
becoming
Okay.
like
Which part is yeah? I mean, can you just maybe in one sentence can you just describe like which part you are not able to like understand? So I understand. I'll go to the definitions also, but before that, I just want to have a little bit of understanding as to you know uh, whether I'm not I'm able to convey what I'm able to what I wish to convey or not. So that part I need to just a little bit of idea. So you understood what killing a mutant is. This definition is this clear? This part, the original definition is this clear at least about killing the mutant,
um,
isn't it?
I think I think
Yeah.
someone. I mean, I would suggest that someone else should explain that part. I mean, I may not be able to explain correctly.
Oh, you will not be able to. Okay, yeah,
Yeah.
fine. That is what I wanted to know. That is okay. That's perfectly fine. We'll go again over that and try to explain. So this is going to be recorded anyway, so this will be helpful
Yes,
for
yes. I
others.
will surely. I will surely rewatch all the sessions.
Yeah, sure. So I think you might not have gone through the previous one. Anyways, that's okay.
Yes, yes.
We'll
I
come back
missed
to it.
the
Yeah,
last two
please feel
sessions.
free to ask any questions whatsoever. Right? It does not matter if you're not able to understand anything. Please ask. Okay. There's no reason to not ask questions. Okay. Always ask, and we'll be happy to clarify any number of times you wish to. Okay. So basically, this was about the final output. I'll see if I can have an example also. Maybe that'll make it. I understand it's all theoretical. Sometimes it becomes difficult to understand. Therefore, we wanted to have a very thorough discussion on this one. Anyway, we'll see if we can have an example also. Okay, so basically, continuing from the discussion that I was having here, so now we refined it, right? So we mentioned the three things are there: reach, infect, and propagate. Now, what we are saying, if you're going to, so still we are trying to kill mutants. The definition is same, but we are having a qualification here. One says strongly killing mutants, okay, and the other says weakly killing. So these are two variants that have come up now. And the difference is what I've described so far. Okay. Strongly killing mutant is the original definition. What we saw here, what we saw earlier also. The output of T on M is different from the output of T on P or the other way. I mean, it's the same thing. Like so, both outputs are different. On the mutant, the output is different. On the program, the mutant is different. For a test case, T. That is what killing the mutant is. Output. Okay, final output. So that is strongly killing the mutant. It is not changed. The same thing. Okay, we've just refined it. We have just qualified it a little bit. It says, given a mutant M belonging to capital M for a ground string program P and a test T is the same definition, okay, as killing mutant earlier. Okay. T is set to strongly kill M if and only if the output of T, the final output, okay, output of T on P is different from the output of T on M. I mean, this part is fine. Okay. So therefore, if I say strongly killing, then strong mutation coverage by definition will be that it'll insist, strong mutation coverage insists that for every mutant that you have to strongly kill every mutant. Now this part is difficult for the reasons we've discussed so far. It is difficult to make the output different every time. Maybe you can do something within the state of the program. Maybe you can affect in some way. Maybe you can change the program in some way, change the behavior in some way. But the output, it might be same, right? Maybe internally something happened, but on the outside you're not able to observe it. So that's what I'll show perhaps with an example. Okay. So strong mutation coverage thereby says I have to strongly kill, which is a strong, a strong criterion anyway, right? Therefore it is called strong. I mean, it's difficult to achieve also. How do you do that for every mutant? Maybe I have hundreds of changes in the code, right? Hundreds of mutants. Now for every mutant, how can I make the output different? It's difficult, right? It's difficult. So SMC is slightly difficult criterion to achieve. Weakly killing mutant says this is the state part. Okay, it's talking about the state. It is not talking about the output. Okay, It is not talking about the final output. It's just saying about the state. And pay attention to this, okay? This is important. So it says given a mutant M belonging to capital M, again the same thing, that modifies a location L. What is the location? Location is somewhere. So if you talk about the source code, then it is some line. Okay. So line number 3, there was this condition x greater than 0. I made it x greater than equal to 0. That is one mutant. At line number 3, I made a change. Okay. So that is the location, line number 3. Okay. Where the mutation happened is the location. So it says weakly killing says that modifies location L in a program and a test C T is set to weakly kill. This is not a strong kill, okay? This is weakly kill M if and only if the state of execution of P, we are talking about the state, not the output, okay? The strong killing, we are talking about the output. If the state of the execution of P on T is different from the state of the execution of M immediately after L, that is, wherever you made the change, because wherever you did not make the change, so for example, I have a 10 line code. Again, I know that this might be slightly abstract, but I'll maybe try to have an example. What I'm saying is that if I have a 10 line function, I have 10 lines in that function, I'm going to mutate that some way. Now I made mutation at line number 5, let's say. For example, I made some change. Line number 5, maybe there was a condition or maybe there was a method call, some kind of thing was happening. Line number 5, I made a change there. Okay, so I got a mutant. Now, so line 1 to 4 is still unchanged. In the ground string, line number 1 is the same as in the mutant is also the same. Line number 2 is also same. Line number 3 is also same. Line number 4 is also same. I made a change in line number 5 only, right? So before that, there cannot be any difference. How can there be difference? Because before that, everything is same, right? It's up until line number 4. So therefore, it says immediately after L. What we have to observe here, what we were doing in the strong killing notion, we were doing what? We were observing the output. Is the output different? No. So mutant is not killed. Is the output different? Yes. If the output is different, the mutant is said to be strongly killed. That is that. Fine. So we are looking only at the output. Here we are saying we are relaxing it. We are saying, okay, don't look at the output. Okay, that is fine. What you have to look for is that wherever you made the change, immediately after that line has been executed, where the change line is executed, is there any change in the state of the program? Is that happening? If that is happening, then in that case you have said to weakly kill the mutant. So this is the refined notion. And similarly, weak mutation coverage should be WMC. I think there is typo here. For each M belonging to capital M, TR contains exactly one requirement to weakly kill M. This was SMC was strongly killing every mutant. Weak mutation coverage is weakly killing every mutant. So strongly killing again is a difficult thing to do. What you can have is weekly killing, you know, on most of them you can do that. Okay, if you have useful mutants, then of course you can do that. Okay, so let me see if I can have a yeah, this is a very good example. So let's see what happens here. With this example, we try to understand what is the difference between strong killing and weakly killing. Because let's start with the normal notion, that is strongly killing. Okay, so for example, how do I put it? So what is happening here is, let me see, this is negative, it is becoming positive, and yeah, okay, so we have a program, and so this delta 4 is where the mutation happened. I've changed it. Okay, this mutation line number 4 is not changed to this. So when you are going to read the mutant, the code for the mutant, when you are going to consider the code for the mutant, you consider this line instead of this line. Okay, so basically what it says is that this line is replaced with delta 4, this line, meaning basically instead of 0 minus x, it became 0. That is, but anyway, let's talk about the ground string now. You're not considering this for now. We just say what this program does first of all. Okay, so we have a boolean is even, and that is going to return a boolean rather. Integer x it takes. Okay, so if it says if x is less than 0, that is if x is negative, then I'm doing x is equal to 0 minus x. Basically, minus x is going to be what? Positive x, right? So basically, every negative number will become positive, right? So I put minus 3 here in the ground string. Okay, forget about this for now. I'm just talking about the ground string. So we have 3 minus 3 is 3. Sorry, if you put minus 3, then x is of course less than 0. So that x is minus 3, right? So you go inside, you make x is equal to minus 3. So x is now positive 3. That is okay, fine. Done. Go to line number 5. So what we are doing is basically checking if it is even or not. Basically, we are dividing, and then you know we are trying to see if the float value is having any decimal points or not. Basically, if it's a whole number, then that is even, right? So any even number, if you divide by 2, then you get a whole number. You won't get decimals, right? However, if there is an odd number that you're going to divide by 2, then you'll get zero point 0.5. So 3 by 2 is 1.5, right? And so on. That happens. So that is what we are checking. Basically checking for whether even or not. That is okay. That is behind the point for now. And number 6, so if that is happening, if that is even, then we return true. If that is not even, let's say for 3, it is not the case, right? So 3 by 2 is 1.5, which is in that case, it will not be same as, uh, for example, if it is 4, then by 2 will be 4.0, right? Sorry, by 2 will be 2.0. That'll be 2 and so on. For any even number, you will go get here and then return true. If it is not the case, then you return false. That is okay. Now, this program is the ground string. I am going to make a change. Okay. So I'm going to change line number 4. What was line number 4? Line number 4 was that if the integer is less than 0, that is if it is negative, then I'm going to make it positive. Minus minus x. Right. Now, in the mutation, in the mutated program, in the mutant, instead of 0 minus x, I made it 0. What is going to happen now? Every negative integer in the mutated program, okay, every negative integer is going to clip to 0. Okay. So minus 3, x becomes 0. Minus 2, x becomes 0. Anything. So here, earlier, what was happening? Earlier, it was becoming positive. So minus 3 becomes plus 3, and minus 4 becomes plus 4, and so on. However, in this case, what is happening? Minus 4 becomes 0. Minus 3 becomes 0. Everything becomes 0 because it should be minus minus is not happening, right? Minus x is not happening here. We just remove this part. We are clipping it to 0. Now, as a result of this, what happens? If you put an even number there, okay, let's say x is 2, rather minus 2, because we made a change here, so we have to consider reachability. Okay, so what happens? What happens if you give 2, positive 2? Here, integer x is positive 2. What will happen? You will not go inside this. X is greater than 0, you'll not go inside this. In that case, what is going to happen? This mutant will not be reached. So reachability will not be satisfied in that case. I'm just saying the cases that are possible, right? One case is that it is positive, therefore you don't even reach it. So in that case, that test case is not useful. Okay. Because the condition says you have to reach it first. Wherever you have made the change, you have to reach it, right? If you're not reaching it, then what's the point making the change? Okay. So in that case, if you want to reach this, then what should we do? What symbolic would say? Symbolic would say I have to satisfy this path constraint to reach it, for example. So here we see, right, we have to have negative. So instead of 2, I'll give minus 2 so that I reach this, so that I reach the mutant. Okay. So I give minus 2. Now what happens in the original program? Original program, it'll go here because it's of course negative, so it'll go here. X will negative x, sorry, negative 2 will become what? Will become positive 2. I'll go to line number 5. I'm talking about the original program. Okay. I'll go to line number 5. I'll do the check for positive, sorry, for even integer. That will happen. So I'll return true. What is the final output? Final output is true in the case of minus 2 in the original program. Okay. Right. Now in the mutated program, what is going to happen? I'm still putting minus
It
2.
will be the same, right? Because
Yeah. Yeah. Because 0 is even.
yeah,
Correct.
both
See,
will return true.
correct. So you got the idea. Basically, in this case, if I put minus 2, then I will not be able to strongly kill the mutant. Okay? Because the output is same, even though something internally, something wrong happened. So the program actually did not check for 2. It actually checked for whether 0 is even or not. Okay? So it might as well be the case with prime numbers. So I'm supposed to give a prime number there, and then I do something in the mutant and then it becomes some other prime number. So for prime number, I return true, but it might not be necessarily the case always. You understand, right? So this is an example. Minus 2, the test case, is an example of not being able to strongly kill. So strong killing is not possible in this case. What happens if I give minus 3? So see, positive cases are not even useful here because you have to get inside, right? The reachability. Reachability says you have to reach the mutant. If you don't reach it, then so therefore you're only considering negative because you have to get inside that you have to have negative. That's okay. What about minus 3? So what happens in the original program? Original program you have minus 3. So minus minus 3 is positive 3. You do this check. This check will result in false. This check will be false because 3 is odd, right? So return false. That is fine. What will happen in the mutant? Now, in the mutant, if you give minus 3, it is going to clip to 0. And the positive check, this thing, the even check will actually return true for minus 3. It should be false. 3 is not even. So this is an example of strongly killing the mutant because you're able to get the final output different. Is the idea clear?
Yes.
Okay. So this was strongly killing the mutant, the original notion of that. What we are saying in weekly killing now, since we are discussing this example, I hope the background is clear so far that I've discussed. So hopefully, I'll continue from here itself. And it might not be a very good example for week killing, but I'm just saying it because we can have it here also. And since the example is already in place, I'll have that. So for example, weekly killing says, so minus three was able to, we are able to show a strong killing. That's fine. Weekly killing, what it says is that wherever you have made the change, location L, okay, if the state of the program, after execution of location, after that, immediately after, executing location L, is different on the mutant than on the, from that of the ground string, then you say weekly killing is achieved. So in this minus two, what was happening? Minus two strong killing was not there. Because if you see final output for minus two is true. Of course, that has to be because two is even after all. Right. And since we are clipping it to zero, in the mutant also we are getting true. It is checking for zero, it is not checking for two, but regardless, we are getting true in both cases. So strong killing is not achieved. We see that. Right. If you consider weak mutation, however, the same test case minus two, if you observe after this, what happens to x? So I'm keeping track of everything, okay? I'm keeping track of x. X is the input here. But I can have other things also, no, in this state. I can have local variables, global variables, and so on and so forth. Maybe I'm having some function call somewhere else. Some variables are there, right? Everything is having its own value and its state and so on. You might have seen state in the symbolic execution discussion as well, right? Concrete state. So everything is having. So if I were to observe it after this, immediately I'm doing it an external observation in some sense, right? I'm trying to log it, let's say, trying to log it. So I have it. Now I go to this part and I'm going to log it. So if I log in the, if I at after line number four, if I were to log or somehow read the value of x in the original program for minus two, the value of x will be at this point at line number four. After line number four, rather after this is executed, the highlighted portion is done now. It's complete. This line is complete. I'm going to move forward. But just before moving forward, I just checked for the value of x. Okay. So for minus two in the original program, it is two because minus two is two. Okay, 0 minus 2 is basically 0 minus 2 is 2, right? It becomes positive. That's okay. In the mutated program, because since line number 4 is this, immediately after this, what will happen to x? X will go to 0. Now, is the state of the program on the mutant different from the state of the program on the ground string? Is that the case? It is of course the case. Because if you are observing x, you're not seeing the final output, okay? We are observing the location at which the change was made. And immediately after that, is the state change? Anyhow, anywhere, any variable need not be the input. In this case x itself is the input, but we are not talking about the input. If it so happens that anything changes in the state, in the memory of the program after that execution, after the execution of the mutant, then we say weak mutation is achieved. Okay, so for this particular code is function, minus 2 is actually a test case for weak mutation, weakly killing this number 4. Delta 4 is what we have. So to weakly kill, minus 2 suffices, but it is not doing strong killing because you see is always true. The final output is true. However, minus 3 is actually strong killing. And you know what? Strongly killing actually subsumes weak killing because you understand, right? Even the output is different. Output is also part of the state in some sense. And again, as I said, you cannot have a final output which is different if you don't have a difference in the state. State has to change first. Infection has to take place first. If infection happens, then only propagation can occur, right? If there's no infection, there's no propagation as well. So therefore, strong mutation coverage actually subsumes weak mutation coverage. So for example, minus 3 was actually doing strong mutation coverage. So that was also weak mutation coverage. But yeah. But minus 2 on the other hand was only able to do weak mutation coverage. If you were to observe at this point, if you were to log x, then you will see that the values are different. Here we are not paying attention to the final output, rather we are paying attention to the location and the state of the program after that. Is this part clear? Any questions so far?
Okay, okay. Actually I was getting. I
Ah,
mean,
go on.
I misinterpreted the code. Like,
Ah,
I read that
hmm.
this code is for finding if it is even,
Mhm,
but
mhm.
I assumed that it was for finding positive.
No, no, this is for
Uh,
is even
yeah,
itself, right?
it is
Right.
for even. Now
Yeah,
it is making sense.
yeah. So you got the idea what we can strong this thing criterion.
Yes, yes, yes.
After this point, if you were to observe, you see the state is different, right? And then it is weak mutation, uh, basically weakly
If
clean.
you could If you could just summarize it in one sentence, I mean, you already did, but if you repeat that sentence,
Yeah, yeah, sure, of course.
difference between them, I mean,
I might as well show you a program maybe.
strong and weak.
Yeah, sure. Let me just have a quick program, short program on this example only, right? I'll have it on Replit. I'll run it. So otherwise, it might become difficult if I don't run it. Just give me one moment, please. I'll run it and show that. That'll be easier. So, okay, I have a Java code here. So what happens is that, uh, okay, I'll just copy it from the slide itself. Okay, so I'll show you what exactly happens. Okay, so this part I understand is slightly difficult to get it in the first, in the first time itself. So that happens. Okay, give me one moment, please. I'll just have the code ready and then share again. This part is important for the exam perspective also because you might expect to see some questions in that regard. Yeah. So what we have is this. Okay, we'll try to understand what happens. Okay, I'm going to share again. Hopefully, is it coming up?
Yes.
Okay, so we'll talk about mutation later. Just comment it out. I just describe the main part, like the ground string. So this is the ground string. Okay, what is going to happen? So I have, let's say, I'm going to print, right? Print, and then I'm going to call is even and print the value of the result, return value of that. Let's say what we have. So 2, right? Yeah, what happens with 2? So positive case, very easy to understand, right? Um, it says it's static. Okay, it should be static. It says, okay, fine, static, fine. So what do you expect? Should give true, right? Because 2 is even. I mean, the easiest case. Just 2 is 2 even. Of course, so you go here, you check that, you get true, right? Or otherwise, let me in fact make it even more easier for you to understand. It's slightly convoluted. So what I will do is, uh, it does not change the uh, what I wish to describe. So we'll have it like this. So what will you do is equal to 0. Now this part is easier to understand. What I'm saying is that if it divides 2, with a 0 remainder, then it is even, right? This is easier to understand. This float and all was slightly confusing. Part clear? Okay. Up until this point, it's clear. I hope. Any question?
No, no, you can continue.
Yeah, sure. Thanks. Now I do -2 also. There's no mutation yet. Okay. I'm just talking about the original program. Nothing is, it's fine. Everything is fine. So nothing happens. 2 is fine. Okay. What about 3? 3 is odd. This is the ground program, the ground string. 3 is not odd. 3 is odd. So therefore false. Fine. -3. Again odd. So should be false. Still false. Fine. Now I am going to make a mutation. How to do mutation? I'm going to change it. Okay. So this is the mutation. I'm going to do that. I'm going to make that change. Okay. So for example, I am having at line number 5, right? So yeah, this thing. I'm going to change it. I'm going to change it to, yeah, rather make it line number 4. So that is fine. Instead of, so this part is where the mutation happens. Okay. Instead of 0 minus 4, 0 minus x, I'm going to have just 0. I make it commented out. That's okay. Basically, minus x is removed from it. So I'm going to clip it to 0. Now let's see what happens to the earlier, the 3 cases that we've seen. So for 2, okay, in fact, I can have all 3. 2, yeah. We'll see it for 2, -2, 3, and -3. 4 cases. So in the mutated program, what is happening? So I'll have to see both actually, but we'll see what happens. So in the in the mutated program, this is a mutated program, right? We have done the mutation. In the mutated program, for 2, the output is true. What was the output in the original program? So in fact, let me have 2 methods. That is not generally what happens, but for just to compare it side by side, okay, I'll have two methods. Okay, so is even original. This is the original, let's say ground, because that is part of the ground string, right? And is even mutated. Okay, so what is the original? What does the original code say? Original code says is x is equal to minus 0 minus x.
Zero
That was,
minus x.
yeah. And the mutated thing, it'll do what? It'll, instead of minus x, it'll have 0. So here you have mutation. So I say this is a portion where mutation happened, because just to understand where the change was. So you understand, right? So we'll see both. So is even, so for example, is even ground and is even. So for both these values, I'll have, and in fact, I can have an x here. Let's make it general enough. Okay, we need it all this. We just remove it and x x. Our intention is to just compare. Okay, what happens in each case. So for example, for two, the output, and this by the way is the final output. Okay, remember that this thing that we are printing here is the final output. Okay, so in fact, yeah, the final output. So what is the final output on for two? For two, what is the final output on ground? Final output is true. For mutated also is true, even though it was clipped to 0. You saw that, right? But this 2 0 was also even, it returned even. So this is not strongly killing. Okay, this part we discussed over the slide also. Okay, now what I'm going to do is I'm going to log also. Okay, or maybe by log I mean I'll just print it. So let's see what happens to x. Here we are observing the final output, but instead of just observing the final output, let us observe x also. Why x? Because we don't have anything else to observe. You only have x, right? No other internal variables. Internal variable you only have x. Nothing else is there. So we'll observe x. What happens to x? Okay, every time. In both the cases rather. So in the after the mutation we'll observe. Because see, wherever the mutation is not there, of course it is going to be same. So why do you compare? You compare only after the mutation has occurred, right? So therefore, after wherever the mutation happened, after that we'll compare in both cases. So line number 4 mutation happened. So line number 5 we are observing just after that, observing that. Okay. Let's see what happens. This is the case for -2. Sorry, this is the case for 2, +2. So this +2, yeah, this is also a nice thing. This +2. So in the +2, uh, actually, +2 case, this was not reached. Okay, this part was not reached because it was 2, right? So greater than 0. So since it was greater than 0, you did not reach that part. So this is only about the, you know, this should only be about the ground, this thing, right? It should not be printed in the mutation, I think. Brackets are missing, therefore it's printing in both cases. Actually, it should be something like this. Basically, we are saying that we are clipping only if the, uh, you know, yeah, it is negative. Yeah. So basically, what will happen? You see only in one case. Yeah, in this case, both the cases you're not reaching this, right? You're not able to reach line number 70 because it is positive. This is obvious. 2 is positive, less than 0 is not satisfied, therefore we are not inside. So this is not useful in that sense. You have to have something that reaches. So therefore our domain is only negative integers now because you have to reach, right? First condition is to reach, then infect, then propagate. Okay, so we are just reaching. First of all to reach, okay, so let's try -2. What happens? So see, there is the difference. In the ground, what is the first one? First one is the ground, right? So let's print it. Okay, ground program. Okay, so this is what we call P in the definition. And in the mutation, what we have? Mutation is called M, right? So the output from the mutation, mutated program rather. This part I think can go here. Yeah. So you see, what is the final output on the ground program for input -2? It's -2, right? Final output is ground program true. Mutation also it is true. However, you see a state was different. Just after the just after the mutation, the value of x was not the same. So therefore, we say weak killing. Weak. Yeah, this particular test case -2 has weakly killed this mutant. Okay, that is what we said in the definition. If we can quickly come back, I think we'll be able to connect the dots now. See, it says given a mutant small m, that is the mutant, right? This is the small m that we're talking about. This part. Okay, I mean, basically the program. Once you change, the entire program becomes the mutant. That is okay. But the mutation has occurred displaced, right? Line number 16 in this case. That's okay. So it says that modifies the location L. This is the location, line number 16. So after that, after line number 16, we are observing what happened. We were observing in both cases because we have to compare, right? So line after the before the like in the ground string also we are comparing that. We are printing that, and in the mutation also we are printing that. That's okay. We'll come back. And program P, a test T is set to weakly kill if and only if the state of execution of P, meaning some internal variable is different. Okay, some internal variable, not the final output. Okay, on T is different from the state of execution of M immediately after L, immediately after that. That is why we are seeing immediately. So line number 4, the change is supposed to happen. So line number 5, I'm immediately checking what is the state now. So line number 16 is the mutation I'm checking now. So I'm comparing these two locations. You see, even though the final output was true in both cases for -2, you are having a different output. Sorry, you are having a different state. You are having a different value for x because of this mutation. And why is this happening? This is happening because of the mutation. If this in the mutated program also, if I go back to the ground string, now both are same. Now in both cases you see 2 2. See, so in this case also you have 2 in this case because no mutation is there, right? I just went back to the ground string. I did a change here now from the ground string. Now you see that these two things are different, even though the final output is same. Now contrast this another case. Okay, so this is an example of weak killing because the final output is not changing, only the internal state is changing. Okay, an example for weakly killing is -3. Now see what happens. In this case, of course, internally the state is different. Instead of getting to 3, because it is 0 minus x has to give us 3 right here, but it is not doing that. It is just clipping it to 0. On top of it, what is more even more different is the final output itself. So in the ground program, because 3 was odd, ground program was correctly saying that it is false. It is not even. It is odd. So therefore false. That's correct. However, since we clipped it to 0 in the mutation, so it got to 0 and 0 is even. So in the mutation, we are getting final output as true. So -3 is actually an example of strong, strongly killing M. Okay. And here x2 -2 was weakly killing because final output is not changing. Is this part clear? Able to understand it so far?
Yes, yes, it is clear.
Okay. Okay. And there's one more case. So one more case is that any positive integer. So for example, index is 2, let's say, or 20 or whatever. So in that case, not mutant or what do you call it? Yeah, mutated location, mutated, right? Yeah, mutated location not reached. Why? Because there's a if condition that checks for negative. We have made change there only. So here is the change right after this. So this mutation, to reach this mutation, you have to have this condition satisfied. So any positive integer will not satisfy reachability. So what happens? In this case, reachability is not satisfied. In this case, infection is satisfied. Reachability and infection is satisfied. So what are we satisfying? In this case, nothing is satisfied. No reachability, so nothing. In this case, reachability, okay. Okay, so in this case, reachability is satisfied. Reachability. Because we are able to reach it. Because it is negative. The chain line, we are able to reach it on this input, right? So negative, we are reaching here. That's okay. Reachability is okay. Then what else we are doing? Infection. Why infection? Because the internal state is different. See, so -2 case minus two also. You had in the ground program 2, in the mutated program 0, right? So infection, reachability, infection, and what else we have? Yeah, and then in this case we have reachability because of course we are reaching in this case also, right? Infection certainly happens, and propagation. Okay, so this is what we have. Propagation says that final output is also changing. Okay, so that's what you have.
Adding another value for the variable x, like, I mean, similar to 20, we can also write any odd numbers, positive odd numbers, and it
Yeah,
should work the same like 20, right?
yeah. So basically, exactly. So okay, it seems to be suggesting. Sometimes it suggests very, sometimes the suggestions are not so good. So sometimes suggestions are good. So I just pressed tab, and it automatically completed that line. Okay, it sees that people are injecting AI everywhere. Okay, fine. So what we are having is, yeah. So for -1
Yeah, you
also,
can change. -1 to 21 or 19, anything.
Any positive number, right? So 21 or
Yeah.
22. What I was
Odd,
saying is
odd number.
odd number, yeah. So
Positive. Yes,
30.
yes.
So two cases for this. Yeah, even odd. And yeah, so the negative case also you have odd and even. So yeah, four cases in total. So in this case, you are weakly killing because you have reached it. Of course, by negative you are reaching it. Infection happens. We see that, right? X is changing. X is not the same. X is different. And in this case, reachability of course happens. Infection happens as well because you have a different state. And in this case, it propagates also. Why? Because we were clipping it to zero, and zero turned out to be even. That is why for odd numbers, so we can flip the case also. How can we flip? Instead of having zero in the mutation, we can make it one. Now, what happens? So it will go to even. It will go to an odd number now. So every negative thing. So you have -3 right here, right? So for -3, let's see what happens. So -3, you'll become weak killing now. It's an example of weak killing. See, we were clipping it to zero. Sorry, one. One is odd. Therefore, in mutation also you are getting false. That is odd. The ground program also says that it is odd. Mutation also says it is odd. But however, it is not checking for three. It is checking for one. Okay. Now in this case, -2 will actually be able to do a strong killing because we are clipping it to an you know odd number. So in that case, yeah. See, the ground program you have true, of course, because true two is even. In the mutated program, however, since it is -2, we are going to one, and in the mutation we have false. The final output is false. So this becomes strongly killing. Then in that case, if this is going like that, but it depends on what kind of mutation we have done. In this case, it was like that, and therefore -2 was only weakly killing. We'll have -3, which will strongly kills. Is the idea clear?
Yes, totally clear.
All right, good.
You,
So,
if you could just
uh
uncomment each line one by one. The three
yeah,
cases,
sure,
rest
sure.
of the three cases. Yeah.
Okay, so yeah, this is the original definition, strongly killing. Okay, so this part is again the terminologies are quite odd, but yeah, we'll go by what has been mentioned. So yeah, so again, we'll go to -2 now. You see, in this case, you can observe what happens. So you see 2 and 0. So of course, infection has occurred. Infection has taken place. Infection and change of state is the same thing. Okay, weakly killing, infection, state of execution, changing. Changing the state of execution is the same thing. These are the three same things. So basically, when we say whether infection has occurred or not, you have to see whether the internal variable has changed or not. Some anything, any internal state is it different or not? You have to compare and check. That is infection. Reachability is the easiest one. You understand whether you are able to even go to that line or not. Right. This is infection and propagation is the final thing. So in this case, propagation is not taking place. See, propagation is not happening because of this change. It is not affecting the final output. It is not propagating to the final output. It is only changing the internal state and not the final output. So in this case, you only have reachability and infection satisfied. Okay. Now we'll go to the third one. And these two are basically in some sense trivial, not trivial, but yeah. Uh, in this case, you'll not be able to reach the mutated portion, so it does not make a difference, right? So it's going to be same always. So for 31 also, it's because we're not checking for that part, right? Negative. It is only for the negative case, right? So yeah, both matching in both cases. It is matching, right? So basically, what we intend to say is that if you want to kill mutant number 4, that is the mutant basically from the slide, this one. At line number 4 it happened, right? If you want to kill this mutant, okay, depending on whether you want to weakly kill or strongly kill, you will have to have a negative integer first of all, so that you reach, you have to have a negative integer, and then you have to have an odd number, so that if it is clipped to 0, uh, you know the final output also propagates and changes the thing. Okay, these are the requirements. Yeah, so you keep it to -3 because it satisfies all three. Yeah, so basically what we are saying is that this test case is not able to kill the mutant. This test case is also not able to kill. So and this one also. This one is able to kill that, but weakly kill that only, not strongly kill that. -2. -3, however, is another test case which is able to strongly kill. Okay. And you see that weakly killing actually subsumes. Sorry, strongly killing actually subsumes weakly killing, because strongly killing, reachability, infection both are happening anyway, which are the requirements for weakly killing. And therefore, I said propagation cannot happen if there is no infection. For propagation to happen, infection must occur. Yeah. All right. That is all there is to it. Yeah.
Yes, now it is all clear. Thank you.
Yeah. Sure. Thank you so much for being here. Yeah. So this part we wanted to cover, I think. Yeah. See, that is what it says. For strong killing, we need the test case to be an odd negative integer. That's what we said. Since 6 and 0 are both even, the decision line number 5 will return true for both the versions. So propagation is not that way. This is weakly killing example, right? Same thing, just checking that, right? So for 6, what happens? So if we are giving -6, then the original program is going to give you 6. Minus minus 6 is 6. The mutated program is going to clip to 0, so therefore 0. However, both are even. Therefore, we get only true for both cases, so propagation is not there. Final output is true in both cases. For strongly killing, the test case should be odd, negative. That is what we discussed. Yeah. And this is the mutation testing process, as in what is the process by which we do. So we have the input program. We are going to create mutants. That is by changing some of the useful things. We apply mutation operators, thereby getting mutants out of that. That's what we do. And there's this equivalence heuristic. So actually, some of the mutants we said that are equivalent, right? Now in complex programs, how do we figure out if you're making a change, is it going to be equivalent or not? Now some of the cases are easy, right? If you're only changing variable names, in that case, of course, that is going to be equivalent because variable names do not matter, right? So you can have that. And however, uh, in the in the complex programs, what can happen is that you might not be able to easily figure out whether that is equivalent or not. So there is some heuristics that we apply to figure out how much of that is equivalent and how much of that is different and so on. And then based upon that, we create the test cases, and then we run T on P, run T on mutants. That's what we said, right? We are going to run T on both the program as well as the mutant. If the output is different and so on, if whether you're able to kill it or not, eliminate ineffective test cases. So whichever test cases are not able to kill your mutants, of course, that are not useful for that particular mutant. It's just specific to that mutant only. It might be the case that these two test cases are useful for some of the mutants that might be there. We have not applied it yet. We have not applied it. We'll see. Maybe these are useful. But for this particular mutant in question that we are doing now, these are ineffective. These are not able to kill it. Right. Similarly, this can kill it. That's okay, but only weakly kill it. Right. If you want to do a strong killing, then you have to go with this. It depends. In some of the cases, it might as well be the case that there are no test cases such that you can strongly kill. Propagation can never occur. It can also happen. Okay. It depends. We don't know. Right. So if there's a method that always returns true or something like that, right, it can happen. But weakly killing, most of the cases it is possible because you have made a change, right? So at that point, at that location, you're expected to see a change. Anyway, so we'll go back. So we are going to eliminate, meaning for that particular mutant, or rather the set of mutants, whatever is not that useful, whatever is not able to kill the mutant, we will not have those test cases. Because why do you test for that? Let's say you have equivalent mutant. Equivalent mutants, so the test cases for that are not useful. I mean, no test cases can basically kill that, right? So you need not have that. And then you have some threshold that how much of how much mutants you want to kill, right? Some you define some criteria based on which you uh, uh, you know of course you have to terminate at some point. You cannot keep doing this, right? Because the space is infinite. You can apply mutation to every line in your program. That is not what happens. You only apply mutation to selected portions of the program where you suspect that there might be a mistake. Let's say talk about conditions, boundary conditions. So you have greater than. It might be a mistake from the programmer's side. Might be that instead of greater than equal to, they wrote greater than only and forgot the equal to. It can happen, right? So therefore, we check only those places wherein there are higher chances of making mistakes, and then basically, so we have a threshold, and if that is reached, then we basically check again all the test cases we run. If all the test cases are passing, in that case fine. If not, then we're going to fix the program again. There must be some mistake in that case, right? So fix again and so on. So we start again. So keep doing this. This is like a cycle that happens. All right. So one question that we skimmed over is that should more than one mutation operator be applied at the same time to create one mutant? This part I think I discussed, right? Are we going to apply multiple mutants? So it says ideally it should be a no. Okay. Experimental and theoretical evidence indicate that it's difficult to track the program behavior when more than one operator is applied, meaning one more than one change at a time. Okay. So two changes if you apply, then how do you figure out which change is causing what effect? This cause and effect you have to figure out, right? Which mutant is causing what change in the state is difficult, right? So you cannot. It is not easy to then figure out which mutant is being killed, by that logic. So therefore, it is we say that you only go to the ground string, make one change, try to come up with a test case so that it is killed, then go back to the ground string, make another change, one at a time only, and not multiple changes. And should every possible application of a mutation operator to be ground string to be considered? No. I mean, it could be yes, but in general, basically you have a lot of mutation operators. So in the practical sense, it is not that useful. You cannot, as I said, right, you cannot apply it to every line in your program, right? I mean, it does not make sense. So what you do is you apply only selected portions. Yeah, basically it depends. So if done in a careful systematic way, there has to be some systematic way by which you are applying it, right? It's not that you are just applying it everywhere. Okay, that is. And then mutation testing for source code is one of the most powerful forms of testing source code. This is slightly newer, not newer, relative to whatever we have discussed so far. Like prior to week 8 was black box. Up until week 7, whatever we discussed, this part about mutation testing is slightly newer, relatively, uh, from those topics. And we need an to generate effective set of test cases. That is the idea. So test cases such that they are able to cover for a lot of mutants, kill a lot of mutants. That is. So then in that case, we are going to see mutation operators that are useful, that are deemed to be useful, for practical purposes in a variety of use cases and applications. So we'll see that maybe in the next one. Yeah. With that, we close for today. I think. If there are any other questions, please feel free to ask.
No, sir, no question. Thank you.
Yeah. Thank you so much, and I think we can close the live stream as well.
Hello.
Hello, Prito. How are you doing?